Welcome back to the workshop. We want to continue looking at limits at a real number, and we want to consider now the theorems for this. The first theorem that we want to take a look at is just some very nice results, very nice manipulations that we can do or assumptions that we can make about limits at a real number. So suppose that we have three functions, f, g, and h, all with a common domain and a codomain of the real numbers. Suppose further that A is an accumulation point of the domain, so that way, as the definition of a limit requires, we can actually take the limit at A. Let's assume further that the limit of f is A, the limit of g is B, and the limit of h is C. Then we have a whole bunch of nice results. First, the limit is unique. Excellent. F must be bounded near x equals a. So wherever we're taking the limit at, as x approaches a, then since there is a limit, f must be bounded. Of course, g and h must also be bounded as well. We also have that the limit of the function minus its limiting value would give us 0. Okay? This is really just a result of, say, part E here. We'll get to that in a moment. Part D is the limit of the absolute value of the function is the absolute value of the limit. Part E is the limit of a sum or difference is the sum or difference of the limits. So if we took the constant function a, then the limit of f of x minus a would be a minus a, giving us 0. So that's exactly the same as C here, or C is a particular case of E rather. And then for f, we have the limit of the product is the product of the limits. And we have that the limit of a function to a power is the limit to a power, okay, where we can let that power be any integer or any rational number. All right. And then we have the limit as x approaches a of a quotient is the quotient of the limits. And then I and j are really quite similar here. The limiting value of a is less than the limiting value of b. Okay? A is less than b, these limiting values, whenever f is less than g. So if f is a function that is less than g, then when we take the limits, of course, the limit of f will be less than the limit of g. Similarly, if f is less than g, which is less than h, then the limit of f will be less than the limit of g, which will be less than the limit of h. So these are some nice results that I think we're all familiar with. This last one is called the squeeze theorem or the sandwich theorem. Everything else should be pretty familiar. All right, excellent. So let's take a look at another theorem. All right, so the next limit that we want to take a look at is an equivalence theorem. Sorry, next theorem. Next theorem we want to take a look at is a statement about equivalency. So if we have some function f defined on some neighborhood of the value a, okay, so we want to take the limit as x approaches a, and we just need f to be defined on some neighborhood. I don't care if it's real numbers or not. All right, so the following are equivalent. The limit is L. And every sequence of real numbers that converges to a, okay, if we take a sequence of numbers that converges to a, then the sequence of evaluations will converge to L. Of course, we don't want all of those numbers to be a itself, because then it would just be f of a. That's not what we want. So if we want things to be interesting, we can just take that none of the values in this sequence are a. But it's also sufficient to say that eventually they're no longer a. Okay? So for every sequence that converges to a, then the sequence of evaluations will converge to L. And that's true for every sequence that converges to A, where it's some sequence of values in the domain. All right? So this will have some benefits. It's not terribly frequent that it's easy to prove this statement, but on occasion we'll use this to prove that. You might find yourself working on a problem where you're like, well, I know something about sequences, and if I could talk about sequences, then I'd be good to go, and you can use that theorem, or this theorem in that case. What's more likely to be useful for us is to actually show that a limit does not exist. So if we can show that for two different sequences, we get two different limits, then of course the limit could not exist. Okay, that's going to be probably the most useful thing for us here. Okay, so this is useful. This is useful for showing a limit does not exist. And again, there will also be some cases in which we'll use some knowledge about sequences to tell us about the function. Now, I'm pretty excited about those situations, but they're pretty rare. So be careful, watch for them, and but for the most part, we'll use the sequences to tell us when a limit does not exist. All right, we have one more theorem that we want to consider. For this theorem, it's somewhat similar to the first theorem that we gave, but in the first theorem that we considered, we had that the limit of f and the limit of g were both finite. In this case, the limit of f is finite, but the limit of g is not. It's an infinite limit. So if we want to consider f and g defined on some deleted neighborhood, so defined on a neighborhood allowing us to take the limits, if the limit of f is finite and the limit of g is infinite, then the limit of the product, we can't really say it's the product of the limits because L times infinity doesn't make sense. But it does make sense for us to say that it must get really big since G gets really big. And of course that's true. The limit of the product is infinity. So this should be pretty clear. This should make quite a bit of sense for us. Not anything too surprising, but it's just a nice reminder for us. And we should also think to ourselves, well, what about other cases? So this is the product, but what about the limit of, as x approaches a, f of x plus or minus g of x? What would that limit be? Or you might consider the limit as x approaches a of f divided by g of x. Okay. So you might also consider these limits as well. What would these end up being? Well, it's similar to what these are, but these I'll leave you to investigate on your own. All right, that's all the theorems that we have for this section. If you have any more curiosity about them, if you have any questions about them or want to talk more about them, of course, those of you that know how to get a hold of me do exactly that, and we can talk about it. Otherwise, I hope you all are having a wonderful day, and I will see you guys back here in the workshop in just a little bit for some examples.